Alright, today we put together the last piece in the puzzle for the culmination of classical electromagnetism, something called Faraday's law. We've been hearing about Faraday all the time. It's about time he gets his name on something. In his experiments, Faraday uncovered the basic law of electromagnetism, which is both powerful and comfortingly simple. A changing magnetic flux through a closed-circuit loop induces an EMF in that loop, and the EMF has a size, which is simply the rate of change of the flux, or it's how fast the flux changes with time. Remember, of course, that this is going to be the change in either, actually any of, the field or the area, or even potentially the angle between them. That's why, for instance, most electric generators work. We spin a loop and we change the angle. We don't change the field strength, we don't change the size of the loop, we change how much of it is on edge with the fields. And the direction of the induced current is given by Lenz's law, which we've covered before. As a reminder, it means the current will flow in such a way as to create a flux that reduces the change in flux that is generating the EMF. As an example, let's take a loop on rails. So we have our conducting rod on conducting rails and being dragged through a field into the board. At this moment, the loop has a side L and a width x, so its area is clearly L times x. So the flux is, of course, since it's aligned with the field, we have that the flux is simply the field times the area, or BLX. Faraday's law then says that the EMF would be the rate of change of that. Sorry, there should have been parentheses there. But of course, the magnetic field is constant and the length is constant, but the width is changing. So we have the magnetic field times the length times the rate at which the width is changing, but that, of course, is just the velocity. So we get that the EMF is B times L times V, which, of course, is exactly what we derived earlier, and that would be disturbing if otherwise. But still, it's good to see that was sort of an accidental application of Faraday's law, and here we can see it's consistent with the actual application. All right, so a loop of wire rests in a uniform magnetic field. The strength of the magnetic field is increasing, inducing a current in a loop. Which action or actions would make the induced current larger, and circle all that apply? So, is it true that increasing the rate at which the magnetic field is increasing would increase the current? Yeah, because it would make dP dt hot larger, makes the rate of change of B larger, which increases the rate of change of the flux. So that would work. Replace the loop with one of larger diameter but the same resistance. Would that work? Yeah, that would work too, because if it's a larger diameter, it has larger area, and although we're not changing the rate at which the field changes, we are changing the area. So the flux would be larger, so the change in flux would be larger, so we get a larger current. That, of course, means that the other way would not work. All right, if we had smaller diameter but the same resistance, then we'd have a smaller change in the flux, and so it would actually be pointing the other way. Delta flux delta T would be smaller. Orient the loop parallel to the magnetic field. That would be bad. That would end up saying the flux would go all the way to zero really, really quickly, and that is not the same change that we have going on, so it wouldn't go in the right direction. And then replace the loop with one of the same radius but lower resistance. So it's the same radius, it's the same field changing at the same rate, so the EMF would be the same, but since the resistance is lower, the current would be larger, which is what we're looking for. So we get something like that. So A, B, and E. All right, consider a metal, let's say a metal sheet, being pulled through a magnetic field as drawn. If we consider imaginary loops in the sheet, we see that the flux is increasing for loops that are entering and decreasing for loops which are leaving the field. Lenz's law implies there should be some EMF that will cause currents to flow, even though there's no well-defined wire. Instead, we get little whirlpools of moving charge called eddy currents, right? Because an eddy, of course, is just a whirl, a swirl, or whirlpool in fluids. And so we get current that loops around like this, get current loops, even though there's no wire that's carrying them. But note that the currents happen to run the same way while in the magnetic field. In other words, this one is going, as viewed from above, clockwise, but this one is going counterclockwise, and when they're in the field, they're both going sort of into the page. So they feel the same direction for the force on them. Let's draw our axes. Oops. So something like this. We have the velocity pointing as shown here, but actually we don't really care about that for the moment. What we care about is we have a magnetic field, and that magnetic field is going from north to south, so it's downward. And we have current, and the current is going into the page. So we know that the current crossed into the field gives us a force which is perpendicular that way. Probably should label these. That's the current, that's the magnetic field, and the force that comes out would be to the left. And that's the case for every one of these lines. No matter which one we picked, while we're in the field, they're all pointing the same way. So they all add, and that force is automatically opposed to the motion. We call this phenomenon magnetic braking. There's a force, even though the sheet is non-magnetic in itself, just the fact that it's metallic allows it to create eddy currents that automatically resist any tendency to move the sheet in. And if the sheet were just in there in any direction we tried to pull it out, it would resist that. It requires an external force to keep the sheet moving. Magnetic braking is important because, again, it's non-mechanical. There's no part grabbing another part, and so it can be used for things that are very hot or very fast. It's a very efficient way of doing it. It's used in a lot of systems to slow rapid engines very quickly without developing too much mechanical heat, and most importantly, very little wear and tear. A similar effect is induced by changing the magnetic field instead of moving the sheet. We use this in something called transcranial magnetic stimulation, which is a cutting-edge neurophysiology topic right now. Magnetic induction is used to stimulate neurons in the brain by changing the flux through essentially a loop. There are both experimental and clinical applications. This often allows a short-term clinical application, has long-term effects. And there are definitely some issues of both privacy and ethics and effectiveness for this, but it's valued by clinicians because it's a non-invasive ability to change the state of the brain. And so you can conceivably do certain kinds of therapies without having to, for instance, cut into the skull. All right. Can there be an induced EMF in a circuit loop where the magnetic field is zero? And the answer is yes. Of course there can, because the field could be momentarily zero as long as it's changing. It could be going, for instance, you could have a field which looks with time something like this, and at this moment the field is zero. But the flux, which is BA, which could be zero, but delta flux over time doesn't have to be zero. Right? It could be just passing through zero. This is like the idea, can a thing undergoing constant acceleration ever be at rest? And the answer is sure. If you throw something straight up in the air at its highest point on the arc, it's at rest, but its velocity is changing, so there's an acceleration. All right, for the next few slides, we're going to explore this situation. We have a uniform magnetic field B that exists in a region of space defined by a circle of radius A, as shown, I guess, not really above. The magnetic field is perpendicular to the page and increases out of the page at a constant rate of 0.4 teslas per second. A single circular loop of wire of negligible resistance and radius of 0.9 meters is connected to a light bulb with a resistance of 5 ohms, and the assembly is placed concentrically around the region of magnetic field, so as shown. Find the EMF induced in the circuit in volts. Well, the EMF, remember, is the rate of change of the flux per time, and the flux is the field times the area. We want delta over delta t. Sorry, that's drawn very badly. So it is the absolute rate of delta BA delta t. But A isn't changing, so it's really delta B over delta t times the area. So we have 0.4 teslas per second. times pi. And then the question is which area? But the area we need is the area that has flux through it. Even though we've got a lot of loop, only this region contributes magnetic field to the flux, and therefore only this region really counts. Imagine thinking of this as a disk in the center where there's magnet plus a ring outside of it where there isn't, and the ring outside of it has no flux. So it's going to be pi times 0.6 meters squared, which turns out to be 0.45 volts. In somewhat less messy handwriting or really print, this is what we get. All right, same setup, and then we want to know which way does the induced current flow. Well, here we have a field which is out of the page and increasing, so we're getting more flux out of the page. We need to generate a field that would have flux into the page, and since we can't change the area here, what has to be is the current has to generate a magnetic field into the page. And if we put our thumb pointing into the page, we find out that we would get a field that looks like this, which is clockwise. Same setup. How large is that current? And after all this magnetism stuff, it turns out this is the easy one. If we do a Kirchhoff's law loop, we start here and we go all the way around. Oops, sorry. We start at the light bulb terminal, we go all the way around, and we come back. Kirchhoff says that that has to be 0, so the EMF from the field minus IR has to be 0. So the current has to be the EMF over the resistance, or 0.45 volts over the 5 ohm. So we get something like 0.09 amp, 090 I suppose. All right, new setup. The experiment is repeated with the loop of radius b equals 0.4 meters placed concentrically in the same field as before, so smaller than the radius of the region. The same light bulb is connected to the loop, and the magnetic field again increases out of the page at a rate of whatever. Neglect any direct effects of the field on the light bulb itself, which is important. Is the bulb brighter in this case or dimmer compared to earlier? Well, we have now less area, but the same rate of change. So we're going to get less EMF. All right, we'll have less A leads to less EMF, which leads to less current, which means dimmer. We would end up with the bulb being dimmer.